Hello, everyone, and welcome back to Active Inference Insights. Today, I have the real pleasure of speaking to Ryan Smith. Ryan is a principal investigator at the Lauria Institute for Brain Research, and he's the research associate professor at Oxley College of Health Sciences at the University of Tulsa. His work focuses on the neuro-computational mechanisms underlying emotion-cognition interactions and how they relate to brain-body interactions, with a special focus on planning, information gain, and interoceptive inference. He is also the primary author of probably the best known and most highly rated tutorial on active inference, writing it alongside Carl Friston and Christopher White. Ryan, thank you for giving me your time. Welcome to the show.
Thanks for having me. Excited to get to talk.
No, it's an absolute pleasure. It's really very exciting. As I said, I mean, obviously I'd come across your work, uh, kind of inevitably for me to have invited you, but it was actually a real treat to sort of go back and go through like what feels like you've done loads and work at this incredible velocity. So it's been really fun to dive in and explore this. I guess what felt like a more empirical side, because I'm spending most of my time reading sort of philosophy papers. So it was
Sure.
great to see some like traditional statistics and some proper empirical work. So it's been great fun on my part. I wanted to start at kind of a pretty broad level and speak about subjective well-being. So you wrote this paper in 2022, sort of grounding subjective well-being in the parameters and mechanisms of active inference. Um, you, alongside Casper Hesp, have come up with this really nice way of grounding well-being in expected free energy. But as you write in that paper, you say, while variational free energy can be understood to track basic biological fitness, this is neither necessary nor sufficient for an individual to report high subjective well-being. So maybe where we could start for the audience is just explaining why the minimization of variational free energy is not sort of the simple solution to obtaining high subjective well-being.
Sure. Yeah, and I mean it's definitely a very kind of complicated and complex topic to jump into, and it honestly depends a little bit about the exact kind of formalism that you're kind of working in. I mean, I almost exclusively work within the sort of like POMDP formalism associated with decision making and planning processes that is the focus of our tutorial. And the focus of the tutorial was very much like trying to get people to a point of being able to do true kind of experimental empirical applications, right? I mean, that's the final section is all kind of meant to transition into that, just because that's primarily what I do. So I mean, with respect to the kind of your question here is that within the POMDP scheme, variational free energy is primarily used as a means of optimizing posterior beliefs about states, right? So it's a state inference sort of process, whereas expected free energy is the thing where you're trying to say, okay, what do I expect the kind of rewardingness of the outcomes to be, and how much information do I expect to gain, conditional on choosing X versus Y. So that there is a true kind of valency thing, right, in the expected free energy, because you have this expected divergence or lack thereof between the things you want and the things you expect, right, under a policy. Whereas the variational free energy is much more a function of, it's just a function of the observations you're getting and how you update beliefs about the most sort of appropriate approximate posterior over those states, right? So in other words, if I perceive that if the observation I'm getting is that, someone's like stabbing me or something, right? Then the process I go through to minimize variational free energy, that is what I use to infer that the best interpretation of what's happening to me is that I'm currently being stabbed, right? So if the idea with variational free energy, as it is, at least in the kind of standard POMDP formalism, is a way of just getting at the best posterior belief about the state you're in, then that state could be something you really like or something you really don't like, right?
Sure.
So just when you see it that way, then there is this kind of big distinction between trying to maximize the consistency between your preferred observations and the observations you think you're going to get. That's valency and could relate to well-being in a much more direct way than just trying to optimize your beliefs about the current states you're in.
Right. It's interesting that you focus more on the sort of perceptual side of variational free energy, because at least the way that I've spoken about it and I've seen written and I've written is that it's kind of dual wieldy in the sense that variational free energy being this kind of upper bound on self information or surprisal, you can also minimize it by taking action. But then that said, when we talk about action, we always frame it within expected free energy terms. So I've been kind of thinking, just again, this is just a completely sort of nascent, not really fleshed out thought, is that action seems to can do variational free energy and expected free energy minimization at the same time, in the sense that, if you're sort of maximization of model evidence term, the minus log of the probability of y, if you're doing that and also you're maximizing pragmatic value, it seems like you're doing both at the same time. Is it kind of an erroneous way of thinking to align or combine expected free energy and variational free energy in this way?
Yeah, I mean, like I said, it's a little bit complex because okay, what's the right way to put this? Certainly, in the what the accuracy of the expected free energy calculation that you do, right, depends, right, on whether you have good posterior beliefs over
Sure.
states, and it depends on whether you're updating your actual generative model appropriately based on the patterns of observations you're getting over time, which would correspond to what we typically call learning, right, as opposed to perception. So obviously, your expected free energy estimates will not be good if your model is really bad. And so there's an indirect dependence, right, on our ability to maximize being in the states that we want to be in. There's a dependence between that and using and minimizing variational free energy, at least in a way that, of course, that depends on whether you're minimizing variational free energy with respect to a model that's in fact accurate, right? I mean, you can get an approximate posterior belief that minimizes variational free energy with respect to a model, but if your model is very mismatched with the world, then
Right.
that approximate posterior is still not going to be a good description of the world, and therefore you might still end up getting observations you really don't want
Yeah.
when
Yeah.
you
Yeah.
choose policies based on that, right? So,
Right.
that being said, I mean, it's a little bit the way you formalize it because the often when it's kind of talked about more generically, especially in the philosophy literature, yeah, definitely variational free energy has the kind of dual right perception action aspect, but there isn't really like I mean, the tricky thing is that action, at least when action is formed in the kind of explicit planning decision making sense,
Mm,
you still do require some kind of cost function, right? You still have to have some mechanism that says, I expect action A to be better than action B.
sure.
Um, and free energy is a function of current observations, right? Whereas the planning and decision making kind of has to be with respect to future observations,
Yes.
and that's kind of the distinction between variational and expected free energy. Now I say that in addition, however, I mean, so you mentioned the thing that me and Casper had done with deeply felt affect paper, and in there is this kind of further term that can be added into the active inference formalism if you want to. It doesn't always kind of have to be there. It depends on the context of the sort of task or cognitive process you care about, or that you're trying to model. But where you are effectively comparing the expected free energy to the variational free energy
Mm,
with the new observation that you get, right? And so there either will be a match or a mismatch there, right?
right.
So if it's the case, for example, and under with that example, if it's the case that the um, the expected free energy gets a little mathy, but the
That's right.
expected free energy vector over policies, if that kind of geometrically, if that vector points in a direction that is consistent with the variational free energy of the observation that you get,
Mm,
right? Then you can kind of think of that as being a little bit kind of like a positive reward prediction error. It's basically
right.
saying that what you got was consistent with and even sort of better than
Yes.
expected, compared to G. So it's kind of like F matches with G or is consistent with G or maybe even a little better. Um,
Nice.
and that in the deeply felt affect formalism, the idea was that sort of positive prediction, yeah, positive reward prediction error effectively can itself be treated as an observation that can kind of feed into a higher level model where it's
Mm,
kind of like evidence for a positive affective state. And
right.
then that can kind of put a prior back down on what the kind of expected value is for the parameter associated with that, which is just this beta hyperprior thing. And
Yes.
the function of that though is interesting, right? Because in the reverse direction, you can also have F disagree with G, right? Which would just mean that, right, your expected free energy was based on a bad model essentially.
Right.
And so in that case, you would expect that there'd be a negative affective response, and so that would act as evidence for this higher level model that would say, okay, that's evidence for a negative affective state. But what that beta term ends up doing, right? So when you negative affective state corresponds to that beta value getting bigger, which ends up being what it does is a little bit nuanced as well, though, because if you don't assume that there's any kind of initial habit like prior beliefs over policies, then effectively all that beta does is just add noise to choice. You could think about it
Mm,
kind of like a random exploration term in like in reinforcement learning, but it's just kind of saying like trust your expected free energy less.
right.
Therefore, select actions a little bit more randomly from your posterior distribution over policies.
Sure.
Um, but if you instead happen to have precise habits, right? So you've just the last 50 times, you were in this situation, you chose option two.
Mm,
And it's kind of assumed implicitly that must have worked out well, right? If you kept doing it over and over again, then if beta gets big, then it ends up essentially favoring the influence of habits over what the expected free energy would say. So in that case, it kind of implies that when you're in a negative affective state, you'll become more kind of habit driven. And so that's a little bit the way that the dynamics end up working.
okay. Excellent. Yeah, yeah, yeah. So maybe just for myself and the audience, I'm going to try and do a sort of paraphrasing slash just trying to align what's going up
Sure,
and no,
sure, yeah,
what
yeah,
kind of what's going up and what's going down.
yeah,
So I'm familiar with the gamma parameter.
yep,
The gamma parameter being sort of a scale of expected free energy estimates. So it kind of tracks in a way how confident the system is in its action model. That's the way that I think
yeah.
about it.
Beta is just the hyperparameter on that. It's just the inverse of that. One over beta
So,
is gamma.
okay. Okay. So that's really useful. So the way that I thought about it is that if you've got lower values of gamma, that means the system has lower confidence in sort of its capacity to do expected free energy, and so it's going to lean towards habits.
Exactly.
Just so I'm aware that that means that it's high beta.
Yeah.
Got it. Okay, so have you seen this new George Dean paper that came out? The preprint came out last week, something like this. It's a
Probably.
wonderful paper. It's about sort of canalized psychopathological behavior. So very much in line with what you're writing about,
Okay.
and exactly what they say. So you can sort of treat gamma itself as a hidden state,
Hmm.
and you can maximize your mental act. You can sort of optimize your mental action so as to kind of optimize gamma in a way. So it kind of looks like, okay, I'm going to avoid thinking about certain memories, or I'm going to avoid thinking about expected, a potential future,
Hmm.
because I know that will lead to reduced gamma, a lower estimate of my capacity to do expected free energy. I may be butchering this. Um,
Yeah, I feel
but
I feel I feel a little limited just because I haven't
sure,
read the paper, so I might not be able to comment confidently on a lot of
sure,
it.
sure, sure. Well, I just wanted to mention it in any case because it's a nice addition to this picture.
Sure. Yeah, and I mean for on our end, yeah, all I can really kind of say is that yeah, for us, or at least the way that we thought about it previously is that gamma itself is not like sort of directly a hidden state itself, but it is like an observation that can act as it's a thing that can be treated as an observation to inform inference over hidden states at a higher level. Um,
Nice.
so
Okay,
you have like
cool.
this kind of higher level that has a posterior over, okay, am I in a positive affective state or I'm in a
Yeah.
negative affective state? And the current and the change in gamma after a new observation is one piece of evidence for changing the positive or negative affective state. Um, Two things that I think are kind of important there, if we're talking about it that way. Again, that's just one
Sure.
idea, but if we're talking about it that way, one is that crucially that kind of implies that it's not the only thing that can act as evidence for the emotional state you're
Yeah.
in, right? So you could have lots of other things besides just this kind of positive or negative prediction error thing that influences, right? Like, I mean, I would think that things about your interoceptive state, right,
Mm.
like are probably important for
Hmm.
that, among other things, right? So I just personally wouldn't want to commit myself to saying that like it's gamma and only gamma is directly
Sure.
right this thing, um, because in that formalism, what ends up happening is just whatever your current belief is at the higher level about your affective state ends up putting a prior back on what gamma is, right?
Right.
So it's like, so when I'm in a negative affective state, going forward on the next trial or the next time I have to make a choice, that thing is pushing gamma down.
Right.
Um, um, Now, I mean, something that I do probably want to highlight though is that I doubt that that's the complete story, for at least a couple of reasons. One big one is that empirically, um, negative affective states, while they are consistent with what would be kind of suggested here, negative affective states track something like lack of confidence in a model.
Hmm.
Um, that being said, typically what that tends to look like in a lot of other sorts of modeling frameworks and some empirical results is that the main effect that has isn't really to make decision making noisier, but actually to like turn up information seeking and to turn up learning rate.
Right.
Right. So it makes sense that if I don't think my model's very good, then I ought to kind of turn
Yeah.
up my
Yeah. Yeah.
learning
Yeah.
rate so
Yeah.
I update my beliefs faster, from the next sequence of events that I experience because I shouldn't be trusting my model well. So it's kind of like, okay, I got to hurry up and change my model to make it accurate again.
Okay.
And this
Cool.
kind of influence of learning rate doesn't directly fall from anything about gamma.
Yeah,
Um,
yeah, 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 yeah. So that's more. I've been thinking about it a little bit as well in terms of canalization. That's more kind of this negotiation between the B matrix and the A matrix. Um, that
Potentially,
I
yeah.
mean, that might be one part of it, right? If I've got
Mhm.
particularly imprecise B matrices, let's say because I have some dopaminergic um,
Mhm.
synaptic misfiring, and so I have hyper precision over A, then I'm going to mistrust these state transitions more than the norm. Let's say.
Yeah, I guess the thing that probably matters here is that, depending on the context that you're trying to model, there's very different things that you might need to be. There's very different parts of your model that you might either want to be or not wanting to be updating.
Right.
Right. So maybe, right, what I'm not confident in is something about my beliefs about state transitions.
Mm.
And in that case, I want to be effectively or directly updating my learning rate about the transition probabilities.
Right. Right.
So I should
Right.
really pay attention to the coincidences between state and next state over and over again to kind of like
Sure.
re-optimize that. Whereas if the thing that I'm not confident about is something more about my likelihood function, right? More about the mapping between states to observations, then I ought to be changing the kind of rate at which I change my beliefs about that likelihood function.
Right.
Um, Now, how you do that itself is tricky. Like I said, I think a more kind of extended formalism would need to be um, put together if we were going to try to turn gamma into something that also affected that.
Yeah.
Um, but it also, I don't know. One kind of tricky thing, I guess, is that in a lot of the kind of practical modeling applications right now, the way that learning rate is adjusted is just via kind of fixed parameter, that's essentially just as a scalar on the updates to the counts and the counts that are added to the Dirichlet distributions, for A or B or whatever one you happen to
Mm.
be modeling learning at a given time. But it's a little bit, I mean, it's similar to, including these sorts of constants, the way you do in like a standard kind of reinforcement learning model. But it's not quite the same as the way you might do it if you were being kind of like trying to be fully true to Bayesian learning, um, because in if you were kind of going true Bayesian learning completely and you didn't want to have a kind of like ad hoc constant, that just kind of
Right.
scales the updates, then it ought to be something that follows from the relative precisions of the your prior and your and the signal coming from the
Yeah.
likelihood, right?
Yeah.
And you can do that, and if you assume a kind of constant sensory input and a constant likelihood, then you would learn more from that signal, given that you had flatter versus sharper priors over states, which would follow from your transition beliefs and therefore your kind of
Right.
B matrix, quote unquote. But that actually kind of, when we've tried to do that in the past, it works, but it's hard to make it work without making a model hierarchical, or at least kind of making it kind of implicitly hierarchical.
Yes.
It's a little tricky, but it formally, the reason for that is that you in the current schemes, observations are kind of treated as things that are um, um, kind of fully like one hot vector, like it's a one and a bunch of zeros. Basically,
Mm.
there's no uncertainty about the observation. Where the uncertainty comes in is just what state you should believe you're in given
Right.
that observation. But
Right.
to get the kind of learning that I'm talking about, you need to actually have the observe. To do it right, in some ways you have to actually have the observation vector itself have some noise in it.
Yeah. 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 Well, because it
To really
does.
get this kind of cross, right? And so that happens naturally in a hierarchical model because the first level states do have noise in them and they act as observations for the second level.
I see.
Um, but also, for practical applications, you can just kind of pretend your model is effectively hierarchical by just having it be single level, but make the observations noisy as opposed
Noisy.
to just being one hot vectors, and it
Interesting.
effectively does the same thing.
Yeah.
Um,
Well, I was thinking it the other way that to control these learning rates, you would need something like a metacognitive aspect. Uh,
mhm. Yeah, you could do something like that too. You could have like a higher level, like a second level state that sort of conditional on that,
right.
whatever that is, it modulates the learning rate at the level below. You
Well,
could
let
do
me
that.
go back to this George Dean paper just because again I'm quite concerned for some reason on well not for some reason it's for good intellectual honesty that I don't misspeak and I don't you know
Sure.
so and I'm sort of curious again about what you think. So I've just got it up here. They say yeah, so in effective inference, the system not only possesses an estimate of action model confidence, described as implicitly metacognitive, but another layer of the generative model can be added so that the confidence estimate itself becomes a hidden state that the system infers using the same mechanics of perceptual inference. So that's kind of similar to, in a sense, what I was saying, right? The gamma itself is becoming the hidden state, but I think the point that they're making there is that you're not just doing perceptual updating, you're also doing planning as inference.
Mm-hmm.
So you can do, in terms of mental action, attentional schemes, you
Mm-hmm.
can deploy certain mental actions such that the observations you make are going to be either, increasing the likelihood of being in that hidden state or not. And
Mm-hmm.
that's what, that's whether that's thinking about something bad that's going to happen in the future or something bad that happened in the past, you're more likely to avoid thinking those things because you're aware that probabilistically you might end up in low gamma.
Yeah, that's interesting. I guess there's a few different things here where I don't know. I mean, my initial
Sure.
go-to when we start talking about all of this is kind of like how I would like, write it down,
Yeah,
and
yeah,
kind of
yeah.
make it kind of, work formally. And so there's kind of like a few different things that are kind of mixed together in there. So I mean, like one thing I could totally see, which I thought was what you were talking about a second ago, was like instead of the gamma-based kind of hierarchical updating thing that we were talking about before, like that kind of second level state, part of its likelihood back down to the first level could also be something about like the learning rate,
Mm,
right? So it could directly, through this kind of additional connection in the second level likelihood, when I'm in a negative affective state, turn up
right,
the learning rate at the lower level, um, which isn't so much intentional or kind of like controlled per
right.
se, right? It's just something that kind of like
Just
happens
happens. Yeah, yeah,
automatically
yeah.
as a function of whatever you infer your affective state is. That's just a little different, I suppose, from if you built in a policy itself that controlled something like the like transitions to like attentional states.
Yes.
So
So
we've done that in some more like emotion inference models, right? Where you could kind of selectively choose, okay, now I'm going to pay attention to my current valence. All right, now
right.
I'm going to pay attention to my arousal level, where you can kind of use a second hidden state factor to kind of like pull out slices of the likelihood tensor that encode the precision of the observations, with respect to the mapping to a different hidden state factor. But so there's that kind of thing. You don't actually need explicit hierarchy for that. You just kind of need separate orthogonal state factors, like in practice. But yeah, so you could do that. And then the third thing I guess it makes me think of is something that I played around with a little bit that I think is actually a really cool idea, but haven't done anything really with,
Mm,
is that you can try to account for like what can still be like a kind of like Bayesian form of like motivated cognition that would look kind of
yep.
biased from the outside by because if in a second level model you're treating the first level states as observations for the second level, then that means like you can have a prior preference distribution over
Yes.
the first level states, right? So then effectively like you actually just like want to believe some things and not others.
Right.
As
Right.
soon as you want to believe some things and not others, then like the optimal policy um, will could be something that looks super anti-Bayesian from a fully like epistemic perspective.
Sure. But probably Bayes optimal under the actual scheme that you've got in place.
Yeah, exactly.
Right.
Right, but externally, right?
Well, yes. I mean, this is exactly the point they're coming to. They speak of sort of avoidant mental action or motivated inattention.
Right,
And this idea is that you're kind of performing the second order inference over the model precision, as I said, but you have this kind of predictive model with model precision as the hidden state, such that, I mean, the way they talk about it is how will I feel if I do that, but with respect to mental action,
sure.
which I think is very, I don't know, I just thought it was very cool and very much
Yeah,
up your
absolutely.
street.
I mean, yeah, when it comes to the affective stuff, I totally agree. Like I said, I'm super interested in this. I mean, I mean, in part it makes me like I both think it's really cool, and it also makes me slightly like empirically uncomfortable. And the reason for that is that like I'm pretty sure it makes like actually testing like whether a model like this is kind of like the best model of human behavior. Basically, I think it makes it kind of unfalsifiable.
Right, 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 right. Well,
because
well,
because then it can account for basically anything.
let's jump into that then. I mean, you when we actually spoke on email, you were keen to sort of mention that you're not just doing pure simulation work, and you're doing empirical, what you call, well, I think what is called empirical computational psychiatry, whereby you fit models to behavioral data
Mhm.
in clinical populations, which is super cool. But I'm not a mathematician, so, and I assume a lot of the audience aren't mathematicians either. So perhaps you could just, in sort of a broad brush approach, describe the distinction between pure simulation work and empirical computational psychiatry.
Yeah, I mean, I guess I think the the cool part about doing simulation stuff is that you're like pretty under constrained, right?
Yeah.
There's a kind of like creativity about it, and you can kind of get really complicated, and it allows you to kind of simulate some cool mechanisms. But a lot of times, like the concern, I suppose, is that they become a lot of like just so stories in a sense, right?
Right.
Like because I could come up with probably like 10 different generative models that would, that would hypothesize somewhat different mechanisms, but they would produce all the kind of like behavioral signatures of the sort of thing we're trying to explain, right?
Right.
So I think it's important to be able to find ways to actually, test, which of these models are actually good, like accurate descriptions of what's actually going on in the brain.
Right.
Um, and so, for that, right, you need to get these models to have direct contact with data somehow. And so usually, so the sort of thing that, we will do, and what I should say, and another thing is that, like how good a model fits data is always a relative comparison, right? I mean, there are absolute metrics of model fit, but usually you want to kind of say, okay, here's a space of possible generative models, that hypothesize different sorts of algorithms that are being used, or different just model structures, but that assume, underlying the same underlying algorithm. And then you kind of want to do like Bayesian model comparison, right? You
Mm.
just want to say, out of all these models, which model does the data provide the most evidence for? Um, and like that actually allows you to be able to test whether or not, like, an active inference model, or what an active inference model would, a given active inference model would predict, actually reproduces the behavior that people actually do, right?
Right.
Um, so I just don't. Yeah, I mean, to be scientific about it, I just wouldn't want, or I think it's important that for people to take, for people outside of just the kind of like active inference community proper, right, to actually kind of take these things seriously and think that they're moving science forward. That we need to be able to actually show that these things are improving, right? How well we can predict what brain and behavior actually look like, compared to lots of other simpler models that have been around for much longer than active inference, right? So I mean, computational psychiatry is a fairly it's a fairly new field, but there's more and more people working in it, but most of them are not coming from like an active inference background. They more tend to focus on simpler reinforcement learning models, that at the end of the day, don't tend to be really too different in what they predict from active inference in a lot of cases. So the trick is kind of finding the right kinds of decision making or behavioral or perceptual tasks to have participants come in and do, whether they be healthy or whether they be patient groups, to try to see. In other words, you have to find tasks where it's clear that a particular active inference model would actually make different predictions than
Sure.
a simpler reinforcement learning model. And we've started to do quite a bit more of that. There's a for anyone who wants to come, a little plug. The One of my current grad students is presenting. Well, she's just about to submit for a talk or a poster for the computational psychiatry conference this summer in Minneapolis in July. And this has been kind of our most thorough attempt at this lately, is we just have a fairly simple like explore exploit, sort of like three-arm bandit task that involves trade-offs between information seeking and reward seeking. And so it does kind of match, right, where active inference is supposed to kind of show its strengths with directed exploration. In this case, primarily with respect to the novelty term, right? So this would be like parameter exploration, not state exploration. But so more or less we have identified, I think, like this is like table essentially of something like 30 different possible RL models and like 30 different equivalent complexity active inference models, something like that. It's a really massive model space. And fit all these models to the to behavioral data and a couple hundred people, and both a Taiwanese sample actually and an American sample, and just done model comparison across these. And the models that tend to win are more complicated models. There's the two kind of best models in what we found so far. One is an active inference model that assumes that people have one forgetting rate, and two separate learning rates for wins and losses, separately. So basically, you update your beliefs more or less when you get a win versus when you get a loss. And then a kind of like dynamic decision noise sort of term that is based on the beta thing, actually based on the updates of the beta gamma term that we were talking about, where effectively what that ends up meaning is that when people get an outcome that's unexpected, right, then gamma goes down, and so the posterior hypothesis flattens out, and so essentially their choices become more exploratory in the randomness sense, when they get outcomes that they weren't expecting.
Right.
If they were negative, if they get outcomes that are better than expected and it's positive, then they become sort of more deterministic in going with what the model would say is the best choice. And so that's the best like active inference model that tends to fit. So it's very complex. It has like 5 or 6 parameters, something like that. And the winning RL model is slightly different. It assumes dynamic learning as opposed to dynamic forgetting, as opposed to dynamic decision noise. But the point is that the main difference between these models ends up not really so much being differences in exploratory behavior, so much as whether or not they include Bayesian forms of learning.
Right, right, right.
So the main thing that active inference does that's really different when you match it to kind of an equivalent complexity RL model is that active inference models are kind of with the Dirichlet distributions. Again, the details of that don't matter for non-mathematical people. It just basically means that in an RL model, you're just kind of updating your beliefs about the expected reward probabilities, whereas in active inference, you're keeping track of those reward probabilities, but also you're keeping track of your confidence in those beliefs about the reward probabilities. And so that's what the kind of take home with it for what she's done is mainly that the ability for the two models to predict behavior is actually the best two models is actually fairly similar, but Bayesian model comparison does select the active inference model over the RL model, and because the differences in accuracy between the models aren't amazingly different, ends up relating probably a little bit more to like complexity cost differences, and kind of evaluation of the independent, like how independent each parameter is in explaining the behavior, things like that. So anyway, I mean, so a lot of what we've been doing is kind of attempting to say, okay, well, how much better does active inference actually do, right? And explaining behavior, is it the kind of most parsimonious accurate explanation for how people actually do make decisions in information seeking contexts? So that's a little bit where kind of the approach that we take, so that, and then using those things by also having people in patient groups with like depression or anxiety or substance use disorders do these same sorts of tasks, and then see whether we can explain clinically relevant differences in these, between patients and healthy comparisons through differences in the actual parameter estimates, right? So maybe it's the case that, so one thing that we have found, right, is that pretty consistently substance users in active inference models tends to show much slower learning rates from negative outcomes than positive outcomes. So it takes a lot more times of them choosing a
Right.
suboptimal thing before they kind of change what they do. Um,
I found that
and
I found that an interesting result. Your 2023 paper, elevated decision uncertainty and reduced avoidance drives in depression, anxiety, and substance use disorders. I may
okay,
be
that's a different one, but yeah.
This might be slightly different, but I found maybe I misinterpreted what you said there, but this idea that individuals, at least with substance use disorders, show a reduced sensitivity to unpleasant stimuli.
Yeah. Okay. So it's yeah. So there's a yeah. So that's a with a different task. It's actually the same sample, but it's a different task.
Right. I guess the prior one is learning rates, right? The first one's learning
Yeah,
rates. Sure.
yeah. So it kind of depends, right? The learning rate one, again, that's with like a bandit task, and so it is about kind of explore, exploit, updating beliefs about reward probabilities, et cetera. Whereas
Right.
the
Right. Okay.
the approach avoidance conflict task is a little different. It's not a learning task; it's purely just kind of a planning, forward-looking task.
Yeah. Yeah. Yeah.
And in that one, it's more or less there's a different kind of number of points that people can win, but they have to also choose to go through some pretty unpleasant affective seeing and hearing some pretty unpleasant affective stimuli at the same time. So you're gonna have to plan whether, okay, do I prefer to kind of move toward the side of this runway that means the probability is higher, I'll kind of get this safe neutral outcome but no points, or whether I expect it to be kind of worth it to me, right, to like under a certain point value try to act in a way that will increase the probability that I'll get the points but also see this super unpleasant stuff.
Right.
And in that case, there's I mean, this is a sort of task that's been used in non-computational modeling ways several times in the past, but the main kind of metric, if you don't do it the computational way, is more or less just this general kind of unidimensional approach avoidance
Sure.
thing. Whereas the modeling version is a little bit more helpful because we can estimate the beta parameter for these people, and then we can also estimate certain things about the shape of their preference distribution. Um, and what that shows, so we can kind of use that to dissociate two different aspects of approach avoidance conflict. One is this kind of like uncertainty about decisions, and the other is this actual kind of approach avoidance drive.
Right.
Um, And yeah, the results for that are actually kind of surprising, because like in the depression, anxiety, and in the substance users, um, they tend to show the patients tend to show greater decision uncertainty, so they have higher beta values, but they actually show more precise preferences for the points, which
Right.
basically means that they're kind of more willing to go through the negative affect stuff
I was
to get
very
those
surprised
points.
by that.
Yeah, so they're actually less avoidant, right? So they're more uncertain, but they're less
Right.
avoidant, and we've
I,
now shown that in 4 studies. So it's a very consistent result across multiple samples.
I read that and I had to read it twice because was really like, I really expected the other way round because we're used to hearing that avoidance
Hmm.
is the kind of number one driver of a psychological disorder like generalized anxiety disorder
Absolutely,
or OCD.
yeah,
So
absolutely.
what do you imagine is going on here? I mean, I think one just talking in terms of very layman non-computational terms,
Yeah.
there's the overexposure of people with psychological disorders to negative stimuli in the first place.
Hmm.
So what's negative for a healthy control is, well, it's all relative, right? And if you've been exposed to overtly negative things like your own emotions over and over again, maybe you have a reduced sensitivity.
Yeah, I mean, we don't really have, like, unfortunately. I mean, our hypothesis going in was absolutely what you said originally, right? That we would get more avoidance in the patient groups. But we were just hoping that the modeling would help us kind of distinguish these couple different kind of dimensions, right, of approach avoidance conflict. But definitely we didn't expect the more approachy stuff in the patient groups. That being said, yeah, so because of that, we don't have kind of a bunch of other. We don't have all the measures that we probably would have gotten to try to dissociate different possible explanations for that kind of unexpected avoidance or unexpected lack of avoidance. Um, so it becomes a little speculative, but one thing is absolutely. I mean, that's one thing you might suspect is what you said, that if people just in general are in this kind of heightened negative affective state, then you know you might expect that makes them more sensitive to other negative affective things, but you also might think they're a little bit habituated to it,
Yes, exactly.
right?
And
So
what
it's
would that
like,
look like in terms of a kind of POMDP scheme? Because I guess we associate habits with action,
mm-hmm,
with the prior value over or prior beliefs over action. When we're
mm-hmm.
talking about habituated responses to stimuli, I mean, I guess it's in a sense action, but what shape does that take?
Yeah, I mean, so like I said, in the official model that we were fitting, it doesn't really include the dynamics of habituation. We're just kind of estimating what the shape of their preference distribution is, right? That to explain their behavior. And so then the explanation just ends up being that they have a more precise preference for winning the points,
Yes.
or a less the magnitude of the probability of the negative outcomes in the preference distribution, which again doesn't really mean probability. It just means they they disprefer the negative stuff less, right? Um, that ends up explaining it, but um, but um, but what would it look like if you included some sort of actual learning dynamics for habituation? I mean, so this kind of habituation is really not so much more about habitual action as it is just the level of sensitivity you have to stimuli, right?
Yes.
So it's a little more, has this flavor of, okay, if I see something over and over again, then my response to it each time is less, right? So
Right.
so
I
I don't
think
know.
you
I mean,
could
I guess
call. I think you could cast that in terms of action. Um, it
well, I mean, so okay, so
I'm thinking in terms of traditional therapeutic responses, right? Like in terms of exposure and response prevention therapy, for example.
um,
You at least have an element of it which said that a dysfunctional avoidance response.
mhm.
Again, this is a non-active inference way of framing it,
Right.
but just in a layman sense, it entrenches the severity or the perception of the severity of the stimulus.
Yeah, so I mean, we have, and I mean, I wouldn't necessarily have expected you to seen it, but if you happen to, I mean, we do have this paper we published a couple of years ago as a simulation paper, specifically on possible mechanisms of CBT. in a POMDP. So we actually did simulate exposure therapy in particular.
Nice.
And but it was the crucial kind of thing we were looking for there was whether or not we could kind of capture, make predictions about the ways that cognitive interventions like reappraisal would interact with behavioral interventions like exposure therapy. And I mean, some of that we ended up being kind of excited about. It seemed consistent with results, or with, when I talk to clinicians, because I work with a lot of clinicians, what they say. But where with that, I mean, the kind of, habituation was much more about, like, so if a person has a strong expectation that, like, if they choose a certain action, then the things they are going to observe are things that they really don't like, right? So things that have a very low preference level. Then, it follows, all else being equal, they're going to take actions that don't lead them to those, to make those observations, right? But the problem is that when those beliefs about the expected outcomes of actions are wrong, right? Then if they just avoid it every time, right, then
Yes.
they can never update their beliefs, right? So I mean, exposure is essentially kind of this kind of like uh, clinician facilitated directed exploration, right? Where,
Right. Right. Right.
they kind of push you to go take this action, right? That's going to make you see, okay, what actually happens when I'm in this state that I've been avoiding. And so the kind of habituation in that sense just ends up being, once they start actually seeing what observations they really get when they're in the
Yeah.
state they've been
Nice.
avoiding, then it just updates their likelihood function, right? It just
Right. Right.
updates
Right.
the
Right.
outcomes
Right.
they expect under that state. But the interesting thing, at least in that paper, was a lot more of how that interacts with your cognitive beliefs. So because you can also, and this is often what happens, right, is that when people go through exposure therapy, they can, even after the negative responses kind of go away, and they start to say, okay, no, I believe, like in the context of spider phobia, for example, like, no, okay, actually, I believe this spider is safe now, right? And so their affective responses like died down. But you bring them back in a couple days later, they see the spider and they have the negative responses again,
Sure.
right? So it doesn't kind of like stick around. It doesn't generalize. And so why is that, right? Because under a simple kind of like unlearning story, they would have just overwritten their old likelihood function, right? So they shouldn't, right? Their generative model should just be different. They shouldn't have those responses again. So what explains that? Well, what explains that has to be that that they don't take evidence, they don't take the evidence from the unexpected outcomes when they see a spider as evidence that their likelihood function was wrong. They take it instead as evidence that they've actually transitioned into a new hidden state context, right?
Ah,
So
nice.
now they believe, okay, I am in the safe context, and then they just update their likelihood under the safe context,
Ah, that's interesting.
right? So then all you have to do is say, okay, well, if there's any uncertainty in the transition function, then even though they believe they're in the safe context now, come back in a couple days later, there's more uncertainty over what context they're in. So the responses come back because the likelihood function under the danger context still says, right, bad things will happen if spider.
So, how would you resolve that?
Yeah, so it I mean, so one thing you want to do then is you want to try your best as a therapist in some way to not use cognitive approaches to try to like make people believe, oh, actually, this is really safe, right?
Yeah, yeah, yeah.
You're gonna
I'm on
go
the
in this
beach.
room, you're gonna see this spider,
Yeah.
but it is safe, right?
Right.
Like you have to have them actually maintain some kind of uncertainty about what context they're in,
Right.
because only in that case, if there's like in the simulations, more or less, like what we showed, is like if you keep the posterior distribution that they have about the context they're in, if you kind of keep that imprecise, right, if you maintain the kind of
Yeah.
cognitive uncertainty, and when they get the unexpected observations that bad things don't happen, then it does overwrite the likelihood under both states, right? Under
Wow.
both hidden contexts, and then it does generalize, right? Um, and that's actually consistent with this kind of cool study that Sam Gershman has written some stuff about. back in like 2015-ish. It's like been a little while, but where you can do more or less the same thing with rats, with like just classical conditioning experiments where, this is kind of, you play a tone, they get shocked, like over and over again with some probability. So now you play the tone and they kind of jump or freeze or do something, implying that they'll
Mhm.
get shocked. And then the standard thing to do during extinction is you just present the tone over and over again. You don't show the shock at all, or you don't give them shock at all. And so then the responses slowly die. But similar to with exposure therapy, you bring the rats back a day later, you play the tone again, and they do have this kind of spontaneous recovery, is what it's called, where they start to have the fear response again. Which means they're doing basically the same thing, right? The rats too are just inferring, okay, I'm not sure if I'm still in the safe context.
Mm.
Uh, so what they showed though is that if you do the extinction time course a little differently, then you can actually prevent this spontaneous recovery. And the way they did it is, instead of during extinction just abruptly completely stopping the association between the tone and the shock, what they did is they just said, okay, for a little while, tone is associated with shock 90% of the time. Okay, now
Mm.
for a while, tone is associated with shock 80% of the time. Okay, now 70% of the
They
time.
taper them off.
Yeah. So, and what that does, you can kind of think about it, is the prediction errors are never that big, right? And if the prediction errors are never that big, then that's not good evidence for the shift in context,
Right.
right? So
Right.
it does cause this slow overwriting, right, of the original likelihood function, as opposed to promoting the state inference thing. And when they did it that way, and then they tested their rats later, they didn't have the spontaneous recovery, like the fear responses didn't come back. Um, and
That is fascinating. It's very
Yeah.
it's quite counterintuitive though,
Mhm.
because I think one would be under the presumption that if you just kept providing evidence, if you kept tying an observation to a different state, that would just become entrenched. But it does make sense that that itself becomes this kind of crystallized thing, and then once you take them out and put them back in, then the previous one still has that precision. that's
Mhm.
that's that's really fascinating. You also said something very interesting there, which was it was kind of under the radar, but the difference between having a strong preference to be somewhere or to have something or to be something or whatever, versus uh like having a strong dispreference not to be somewhere, be something, have something.
Mhm.
So a positive versus a double negative.
Mhm.
I've often found this in active inference that I don't think it's been particularly well codified what the difference is between those. So people say, oh, I want to be 37.8, right, in some subpersonal way, I want to be 37.8 degrees Celsius, and so I take action to restore that. But you could well cast that as I don't want to be 40 degrees Celsius,
Yeah.
right? Is there a technical difference between those?
So I mean, one thing that I guess is kind of unique about the way that active inference encodes preferences compared to, more kind of like traditional formalisms like reinforcement learning that cast things explicitly in terms of reward function, is that, strictly speaking, an active inference agent isn't really trying to maximize reward. They're trying to minimize divergence from a target distribution,
Right.
right? And that actually has certain interesting implications. But one thing to consider with that, though, is that unlike in things like reinforcement learning, um, all of your preferences kind of constrain each other in the sense that the whole distribution has to add up to one,
Mm.
right? Um, so you can. So I think that you will have to kind of, relatively speaking, um, basically, you will only be able to specify relative preferences. Um,
Right.
so I think that if you have a preference distribution where the kind of highest mass is over, like 38-ish degrees, right? Then the fact that it kind of tails off on both sides simultaneously guarantees that you disprefer being
Yeah.
above or below that. Um, so I don't know explicitly whether or not there's any way to encode those in a way different. There are interesting things you can do by putting kind of like negative preferences for something and positive preferences for another thing. If there's like an observation you can lock as kind of like a baseline value of like 0, um, when the thing gets normalized, to turn it back into an actual probability distribution, then it does still end up being kind of a precise preference for one thing and dispreference for the other, and they do still end up being relative to each other,
Mm.
though. So, and the main thing that we tend to see when we do like simulation stuff and those sorts of settings is it just tends to lead to this kind of like anti-exploration behavior. When one thing's really negative, where it's kind of like the agent is just kind of this like better safe than sorry
Right,
sort of
right,
very
right.
conservative behavior. But I think there should definitely be ways of encoding those in terms of all just kind of relative positive values that end up normalizing to the same distribution.
Cool. Yeah, I think part of the reason why I asked that is because I think it's a point that you make in the papers that you've written on interoceptive inference,
Hmm.
which is that when we speak of sort of so-called aberrant interoceptive inference, a lot of papers are not very clear whether they're talking about the underweighting of priors or the overweighting of the likelihood distribution.
Sure.
I think part of the problem is people think of precision weighting as like a necessary zero sum game, such
Hmm.
that you can't have both.
Hmm.
So if I have reduced precision over my likelihood, by necessity, that will lead to increased precision over my prior. If I have decreased precision over my prior, by necessity, that leads to an uptake in the precision of the likelihood. But what you show, at least in this 2020 paper, the one that I read from PLOS, where you
Hmm.
did the interoceptive perturbation condition, is that this
Yeah.
isn't the case. So where do you think that kind of false intuition comes from?
Oh
That
well, it comes from the fact that people usually, in the way that they, at least in these more kind of conceptual papers, comes in part from the fact that these are under they're talking about models that have Gaussian assumptions with continuous distributions. Because if you just have along a single dimension, right? If you have like a distribution that defines the likelihood function and a distribution that defines the prior belief, then there are, right, when I turn up one or turn down the other, then there's a bunch of different ways that I can kind of combine those things to lead to the same posterior. So it does become hard to distinguish. So it depends on the dimensionality and depends on whether you're talking about continuous or categorical distributions.
nice.
So in the case of what we're doing, these are discrete distributions, right? So in discrete models with the dimensionality the way that we have it set up, it makes they make clearly distinct behavioral predictions. But in the kind of unidimensional Gaussian setup, then you do get this more only the relative weighting matters.
Yeah, yeah. That makes sense. Okay, so thus far, I know we haven't got too much time, but thus far, I know we've kind of been speaking generally about perceptual updating and parameter updating,
Hmm.
or parameter learning and belief updating. But we also have structure learning and active inference. And I think you make a really nice point to say that sort of something like introducing a concept to distinguish between or to yes to let's say split up a concept that you had before. So if I had anger, now maybe I can turn that into rage and fury.
Sure.
um I believe you call that emotional granularity.
Yeah, in the emotional state inference context, yeah, we would talk about that in terms of granularity, or yeah, that's usually probably the best way to talk about it. Yeah.
It's a really fascinating concept because it I think on first glance it seems like a sort of just linear benefit. The more emotional granularity I have, the better.
Yeah, I mean, what the direct relationship would be between like the number of states in a state space and something to do with gamma, I think is going to be fairly indirect, but for a number of reasons. But I mean, I think with most things, right? I mean, the general answer is going to be that it's not so much about complexity per se as more complexity than necessary,
Yeah,
right?
yeah,
So right, adding complexity is good if it increases accuracy, right?
right, right,
So
right.
so so what it would mean, right, to be more complex than necessary would be that there's a mismatch to the actual generative process. So I think that the if you have more, right, if you're overfitting, right, to the generative process, right, if you're inventing more categories than there actually are distinctions to make, then obviously that's going to be problematic, right, because you're going to think you have more information than actually you do. Um, but so long as you're carving up your state space in a more fine grained way, and that actually does add to the informativeness of the information that your generative model is able to kind of pick up and then use to inform policy selection, then I would expect it would be the more the better, right? It's just the more, so it's the more accurate information you have, the more informed policy selection will be, right? So
Sure.
as long as you have, you're good at inferring the right, posterior over what emotional state you're in, and each emotional state that you kind of have acquired into your generative model, if each of those does in fact make unique predictions about patterns of current and future observations under that state, then yeah, I mean, it'll be better just because it'll should, right, on average, just make policy selection more informed.
Right, right,
Um,
right.
but
Do
yeah.
you, thinking more broadly about the distinction between structure learning and parameter learning, do you see these as bright dividing lines, or do you see them as being kind of philosophically vague as to when parameter learning becomes structure learning?
Like, I guess it's just tricky. I mean, like, you get in the weeds with some of this stuff because
So you do.
people
That's
use
what we're
people
here
use
for. We're here for the
people use
weeds.
people use structural learning, the term structural learning, to mean several different things, right? So I mean, structural learning itself is a kind of like superordinate category with a bunch of different kind of exemplar things within it. So I mean, we did. I don't know if you saw this one paper on structural learning specifically that we
Yeah.
put out a few years ago, where it was kind of like people that there was just like kind of a dumb example of people trying to like learn like coarse grained or fine grained different types of like birds and fish and stuff,
Right, right, right.
right?
Yeah, yeah, yeah.
And so in that, it was like you could just learn like these broad categories of bird and fish, or you could kind of like learn to carve it up into specific types of birds, specific types of fish, and they just kind of, each of those was defined with respect to specific like patterns of covariance among certain sorts of observable features, right? Like wings versus gills and size and color and things like that. But and in that particular case, the way that like structure learning was posed was in relation to kind of like inferring how many states need to be in your state space, right, to account for data. And so that has to do with kind of the setup of the structure of the generative model proper, right? Like how many types of states, how many state factors, how many levels of states within each state factor, etc. So in the general POMDP scheme, that is distinguishable from parameter learning in the sense that parameters are usually kind of the values of the entries into the matrices within things like the likelihood function, transition
Sure.
function, etc. That you update, but you update those under the assumption that like number of columns in each matrix are kind of fixed, right?
Right, right.
So if you're talking about kind of this granularity, kind of fine graining of the concepts that you have, then there is a clear distinction between those examples of parameter learning and structural learning. But like I said, there's other types of structural learning, and the actual implementation of how you do structural learning also matters because in our example, we use this kind of like little trick, right, where we just kind of said, we're actually gonna stick the matrices in as though there's a bunch of these kind of extra unused columns, so we didn't have to kind of like explicitly add states to the state space. We just kind of had a bunch of states that were just kind of like sitting there silently unused.
Yeah.
And then the way that the thing kind of worked was just that what they meant to be unused was the distributions were just completely flat, right? So they didn't predict really anything unique about the observations.
Sure.
And so the way that would work is just that more or less that if you got some pattern of observations, that was consistent with one of the kind of informative likelihood functions under a kind of state that you already had, then the posterior would be precise over that state, and you would have a basically zero posterior over all the unused columns, and so you wouldn't have any parameter updating under those columns. But if you had some pattern of observations and they were really inconsistent with any of the informative mappings that you had, then effectively what that would do is it would mean that the flat mappings would better explain the data.
Right.
And as soon as like the flat mapping better explains the data, then you end up with a precise posterior over one of these unused columns, right? Whichever one happens to explain it best. And then you just start learning the parameters under that new column, right? So and then that's just a way of learning a new informative mapping. So it's kind of like effectively now you have a new column, you've expanded your state space, right?
Yeah.
And you could do that a little bit more explicitly than we did by writing in some additional function that like explicitly, just like added new columns to the state space or something, as opposed to just having these unused ones sitting around.
Right.
But my point is that the relationship between structural learning and parameter learning is they're very tightly intertwined in that case, right? Because like when you start learning the parameters, like the thing that leads you to start learning parameters is the exact thing that is causing you to do structural learning.
Right. Yes, exactly.
So,
Yes.
but again, I
Yeah,
mean,
you can't really.
that's one implementation, right? So I'm saying that won't be true. That doesn't need to be true generically, but that will be true in some cases.
Yeah. Well, and it seems like they all lean on one another in some kind of recursive manner where you can't really have structure learning without learning the parameters of that structure in the first place, nor the belief updating that allows you to kind of get there in the first place, right? In a dynamic system, in a dynamically changing system.
Yeah, I mean, I think it's just, and again, I can't really say with confidence how well this will generalize to other cases of structural learning, or even just other kind of generative model setups and things like that. But yeah, at least in this case, it's kind of you have to effectively infer that the current informative parameters and parameter based mappings that you have are not doing a good job of explaining something, and then end up with a very low posterior distribution over or a posterior that assigns a very low probability to any of the states you currently have in your state space. And then so it's like you get the right posterior based on the fact that your current parameters are not good don't provide good explanations for the data, and then by starting to update different set of parameters, you end up leading to doing something that is effectively structural learning. So they're just very, it is all just very kind of tightly connected.
Yeah. Well, it'd be interesting to see if you could sort of disambiguate them, in a model, like whether you could just have. I guess there's that.
Yeah, conceptually though, I think that's tricky, right? Because you somehow have to say, I need structural learning only because
Well, exactly. Well,
my
that's what
current
I meant
model
kind of
isn't
by this
doing a good
recursive
job.
nature. I mean, I
Yeah,
don't know if recursion's even the right way of talking about it. It might be sort of nesting, um, in some sense that belief updating drives parameter updating, which like ultimately feeds into structure learning.
yeah.
Yeah. Cool. So, final question, big
Okay.
question. You got this paper coming out, the so-called empirical status of predictive coding
And active inference, but
and active inference. Yes, is that the whole name of the paper?
yeah.
Okay.
Yeah.
Um, it's a sort of classic critique leveraged active inference that it's self-contained and it's an echo chamber and it's a lot of philosophers and mathematicians kind of spitballing these fancy ideas, but it doesn't. This is a common critique. I'm not saying it's true.
Oh, okay. Yeah.
Yeah. Oh well, it would be odd if I were to promulgate that position as the host of this podcast.
Oh, no. Sorry, I thought you were saying that was the thrust of our paper. It's like
No. I'm saying it's a common critique from those on
I
the
was like, I don't
outside.
remember saying all of that.
No. I know you didn't, but it's a common critique. At least, I mean, that might be oversimplifying the critique, but that this theory of everything is overgeneralizing and it doesn't have an evidential basis. Where, having done this sort of deep dive into the empirical status of active inference and predictive coding, what are the conclusions that you guys have drawn?
Um, I mean, I just think I kind of think at the end of the day, I mean, it amounts to be something kind of similar to what I think you'll see in a lot of review papers for most things, right? Is just that there's a lot of stuff where more work needs to be done
Sure.
for it to be definitive. I mean, that's kind of like the very oversimplified conclusion. I mean, I would say that I mean, one thing that I hope that we tried to make clear is just it's more that like there's just lots of different levels of claims with respect to both predictive coding and active inference, and they all kind of need to be tested in a way that's a little bit at least partially independent of each other, right? So I mean, especially in the philosophy literature, people will even talk about really broad like categories like, just like predictive processing,
Yeah.
quote unquote. But like, I mean, if you want to move from that down to stuff that is actually testable, requires a bunch of there's a bunch of kind of layers that you have to kind of work through to get there, right? So you kind of say, okay, well, predictive processing, it's a very generic idea that in some way one of the main things the brain does is predict stuff, I guess. Right? That's like, okay, well, two of the most kind of like prominent, but certainly not the only possible categories for that are like predictive coding and perception and
Hmm.
active inference and action. But
Hmm.
then even from there, right? I mean, like predictive coding makes particular um, explain or makes particular predictions if what you're talking about is um, something about the predictive coding algorithm, right, as defined, right, which doesn't necessarily need to make predictions at the level of the kind of like neurobiological implementation, right?
Right.
So, and same thing with active inference, right? Active inference. First, say, okay, well, what type of active inference are we talking about? Are we talking about like the continuous state spaces? Are we talking about discrete state spaces? And like, are we talking about commitments related to some of these like claims about the gamma stuff and dopamine, or are we just talking about things about categorical state inference, and that depends on minimizing variational free energy through like a variational message passing scheme, right? And okay, are we actually hypothesizing variational message passing, or are we hypothesizing marginal message passing, or are we hypothesizing that the implementation draws or that the algorithm is doing some sort of like belief propagation thing, right? And then even there, right, that's still all just at the algorithmic level. And then you have to say, okay, well, if I commit to some algorithm, right, if I commit to POMDP, discrete state space, this particular generative model structure for this task, um, with this message passing scheme, as I said, then all right, there's like probably at least like 20 ways that you could set up a neural network, right, to solve that, right? So
Right.
then you also have to have a hypothesis about, okay, what implementation, am I testing, right? And what are the predictions of that implementation, right? So if I'm doing something at the neuroscience level, then I'm gonna say, okay, it's kind of this very kind of hierarchical thing where it's like, this particular neural prediction that follows from this hypothesized neural implementation that follows from this specific narrow algorithmic commitment, like from this larger kind of framework,
Yeah.
you know what I'm saying? So it's like,
You start making exclusions.
yeah. So testing these things what it even means to be testing these things is kind of complicated because by the time you can actually get down to something that's empirically testable, you've narrowed it down a ton. Um,
Right. Right.
and ruling
Right.
out one implementation doesn't falsify,
Yeah. Yeah. Yeah.
predictive processing, nor does it falsify active inference, right? It just means you ruled out that a particular implementation of a particular algorithm, within the active inference framework, et cetera. So it's like, okay, well, now on testing like implementation hypothesis two.
Yes.
So it's so that's tough, right? So then, but a lot of what's been done is much more, well, I should say with predictive coding, a lot of stuff's been done at the neural level. With active inference, it's very minimal has been done in terms of like neuroscience, neuroscientific studies. Like Philip Schwartenbeck had a cool study in like 2015 where they did some of the like midbrain dopamine um, results in relation to some of the beta updating stuff. I mean, it's called alpha in that paper, so like slightly older formalism, but same basic idea. Um, but so there's that, and then there's kind of like with predictive coding, for example. I think many people would say that one specific commitment, at least to kind of like vanilla forms of hypothesized predictive coding architectures, is like, okay, well, prediction errors get passed upward, predictions get passed downward. There's kind of these separate populations of prediction units and prediction error units.
Yeah.
Typically, it's like, okay, well, the prediction error units are in like cortical layer 2-3, and like in the deep prediction units are in pyramidal cells in layer 5 and 6. But then when you actually look at like some of these more complicated like canonical microcircuit models and things like that 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 really explore in detail, right, how you would do predictive coding in a way that would kind of match up to the actual like cortical columnar architectures that we know about, from like microanatomical, actual brain studies. Like, I mean, it becomes way more complicated, right? You have like specific roles of like granule cells, and then you have kind of like the sorts of predictions and prediction errors that are hypothesized to be like passed around through like different interneurons, and then how those pass signals up. And, it turns out that prediction error signals need to be inhibitory, but the between column connections are all glutamatergic, and so they're excitatory, right? So you need to basically have any prediction error signal be excitatory, but then pass through some inhibitory interneuron at the receiving end to then turn it into right an inhibitory thing. And then as opposed to the simple kind of vanilla predictive coding architectures or algorithm, the most of the canonical microcircuit stuff has been pitched in terms of these more kind of like temporally extended versions of predictive coding, where you have like at each level you're not just representing a hidden state, but you're also representing what they call like a hidden cause. And the distinction between a hidden state and a hidden cause is that like one of them actually predicts the dynamics of the states at the level below. So it's kind of like hidden states to say like hidden state is, or now I'm mixing up which one it is. One of them, either hidden state or hidden cause. I mean, this is just very jargony,
Yeah. Yeah.
it just arbitrary choice of terminology to a certain extent, but well, I'll say it the way that's a little more intuitive to me. But so if hidden state is like birds singing a song,
Mm-hmm.
right, at one level, then I just have some representation about probability of birds singing song or something like that, fairly abstract. But then that then sends a signal to represent this hidden cause thing, and what the hidden cause thing does is send predictions down to the level below about like some series of notes, right?
Yeah.
Like in some sequence to the level where the hidden state at that level is like representing what note is happening in a unit, at some time period. But so even there, right? Those are both predictive coding, but those are two
Yeah. Yeah. Yeah.
different predictive coding theories. Um, so so anyway, I mean, so just to point out fairly long-windedly that there's just a lot of complexity in specifying what you're in fact even testing. But the main thing, I mean, the main kind of broad strokes result was just that in predictive coding, I mean, there's certainly nothing that rules it out, right? I mean, there's some cool results, probably like the strongest results that would suggest something like that has to be going on is like findings related to like omission responses, right, where brain activity increases when you expect to get a stimulus and the stimulus is absent,
Yeah.
right? So like if a stimulus comes, right, it should trigger some activity under a feed forward sort of hypothesis, but the absence of something should never trigger,
Yeah. 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 That's
you know,
just sort of classic
case, right?
Schultz and Montague
Yeah,
raw prediction error stuff.
so but emission responses and other things like error related negativity and a lot of the kind of more standard stuff that looks like prediction and prediction error responses that are consistent with predictive coding, they certainly don't provide really precise evidence that there's like particular layer 2-3 neurons that are representing prediction errors and 5-6 ones that are coding predictions. There are a couple cool studies that have come out like super recently though that do look like with like laminar fMRI and things like that are starting to support these kind of like distinct populations of error neurons and prediction neurons. So that stuff's exciting. Um,
It's all very
and
exciting. Well, it's a niche, but at least it's incorporating. Well, at least it sounds like from your investigation, it's beginning to. Well, I'd like to think that it's beginning to hone down on some specific ways that we can get more precise hypotheses and ways of testing those hypotheses. I mean, you know, if the main paper is 2009, 2010, fair enough that it's taken a little while to get its, you know, to start reaching that kind of finer precision, that
Sure.
level of granularity, that level of, I think, to my eyes, some of that philosophical work needed to be done just to lay out exactly the parameters, if you pardon the pun, of the explorandum of what we're trying to find out. So I don't know. It sounds promising to me. Sounds exciting.
Yeah, no, I mean, I think, yeah, I mean, certainly, I think we need to hold things to given, I mean, as you say, right, given that these, these particular theories are, much more recent, right, than other like, computational neuroscience theories that have had a lot more time, right, to be tested. So yeah, I mean, I think we need to be fair given the amount of time that these things have even been around to test, and the number of groups that have been motivated to, put together studies and get them funded, right, to do these sorts of tests. Absolutely. I mean, and with respect to active inference, I mean, that's even more true, right? I mean, the actual kind of like empirically testable like behavioral modeling, sorts of sufficiently precise, right, formalisms for like the kind of stuff that we do, that's been around like what, since like 2017,
Yeah, yeah.
ish, and it's been kind of evolving from there, and so much less time even. And I mean, I think there's a lot of things that I mean, we still need to do, I mean, along the approach that we're taking, right? So I mean, primarily, what we've the stuff that we review that that we have done with like trying to find empirical support for active inference, probably hasn't really up until now done a good enough job of doing model comparison against competing models. Our focus has been largely kind of like computational psychiatry focused. So the idea has been more, okay, let's define a set of active inference models, fit those models to behavior, and see where we can find differences in those models between clinical groups and healthy groups, right? So we can show that, like, in an absolute sense, right, like active inference models can explain data reasonably well, right? Like
Yeah.
on a model, on a task where like chance action probability would be like 1/3, like these models can explain behavior with assigning probabilities around like between like 0.65 and 0.7 something, right? So I mean, it's much better than chance, and not too different than what you'd see in other computational neuroscience studies. But that doesn't directly compare active inference models to other classes of models, right, that have already been around, right? And so that's a little bit more the kind of thing we've been trying to do recently, is to more definitively kind of say, how much can we find evidence for active inference models that is not equal evidence for other models that have been around for longer.
Yeah.
And
No,
so
that sounds,
yeah.
it sounds absolutely worthwhile. And yeah, I think some people are, you know, they almost don't want to do that, because if it turns out that an RL model does better than an active inference model, then like let's just throw in the towel. But it's
Yeah, even that I think needs to be kind of like understood with a little bit of a grain of salt, though, because well, you can worry that there are tasks where the tasks are simple enough that an RL model will do a perfectly good job explaining what's going on, and an active inference model would basically predict the exact same thing,
right.
right, as a reinforcement learning model. And in that case, maybe the active inference model is more complicated, and so
Yeah,
like
yeah,
an
yeah,
RL model
yeah,
could
yeah,
win. But I mean, that's just because in those contexts they have a certain isomorphism,
yeah,
to them
yeah.
So I think you have to make these comparisons in tasks where like a simpler model certainly could explain behavior equally well, but there's reason to think other models that there could be the patterns of dynamics in the choice behavior that could differentiate, right, active inference models from
I like it,
reinforcement
Ryan. I like it. You're staying true to the field. I like it. It's good. It's that loyalty is much needed. But no, I really do admire the intellectual rigor and the academic rigor. It's much needed.
Yeah, and I certainly wouldn't want to like say, like our stuff and only our stuff. I mean, there are other people that are doing, very recently that have been doing really cool stuff. Like there's this, like the first author's last name, like Gidson or something like that. I can't remember. Sam Gidson, maybe. I don't quote me on that, but they did this really cool study where they took like these two, a couple, or maybe it was like four. I think it was, yeah, four different like publicly available data sets from on the two-step task. Two-step task is a very kind of classic RL task that like basically was designed specifically to estimate how much people are doing more kind of like model-based versus model-free sorts of planning.
Mhm.
Um, and I mean, super widely used. I mean, people have shown really cool stuff with it. Developmentally, like kids as they get older start to look more model based.
Right,
Things like
right,
that.
right.
Basically means they actually start to use an actual transition function,
Yeah,
right?
yeah, yeah.
More, right? And but so what they did is they took, right, like the classic, widely used model based, model free kind of combo model that typically gets used for that task, and then they also fit that same data to like a competing active inference model. And in two of the four data sets, model comparison was kind of equivocal. And in the other two data sets, active inference models did win in model comparison for that. And these are pretty large data sets. And again, it's another, very kind of classic task. So the fact that active inference did a better job of explaining two-step task behavior, I thought that was actually like
Yeah,
incredibly
yeah, yeah. No, well,
incredibly
yeah. I mean, when it starts
better
infiltrating,
better than what we've done in terms of actually testing active inference models.
yeah. Well, when it starts entering into the space where others should dominate, you know, that's when you know it's onto something. Ryan, I know you're the world's busiest man, filling out forms and all sorts. And so I'm incredibly appreciative. We've just hit the hour and a half mark. Well, thank you so much for giving me your time and educating me. I mean, every time I have people on, whether they're philosophers, neuroscientists, mathematicians, and so on, it's always such a pleasure to learn more about the work they're doing. In terms of what you've got coming up, of it, so this paper that is coming out in the future, that's out. People can read it, although it's supposedly out in the future. What else? What else have you got coming up? Where can people find your work? How can people reach out to you if they're interested in asking questions or collaborating or whatever it might be?
Oh yeah, I mean, anything on our lab website, or email me, like rsmith at laureateinstitute.org. Feel free.
We'll
Message
link
me.
we'll
Yeah,
link the lab.
DM me over Twitter. I mean, any I
You
don't
know
know.
the typical routes.
All the standard stuff. I mean, my email is also typically the one that's like the corresponding author email in most papers. So, and there's certainly lots. Lots of ways to get in contact with you, so desire. But
Great. Well, we'll
um,
make sure we link everything below. So thank you once again from me and the Institute. It's been really, really fun.
sure, no, thank you very much for having me.